Welcome to Ask and Learn.
So in this problem, for the first part, we are going to take the mass of the alcohol given and then divide by the molar mass of the isopropyl alcohol. Then we have the moles of alcohol, and from the balanced chemical reaction, you see that 3 moles of alcohol react with 1 mole of the sodium dichromate. So we're going to use that mole ratio to convert from moles of the isopropyl alcohol to moles of sodium dichromate. Then in 1 mole of sodium dichromate dihydrate, we have 1 mole of sodium dichromate. So we can use that mole ratio to convert to moles of sodium dichromate dihydrate. So then we need to calculate the molar mass of the disodium dichromate, or the sodium dichromate dihydrate. So therefore, just multiply by the molar mass of the dihydrate, and then we'll end up with the mass of the dihydrate that is needed to react with the isopropyl alcohol. So now we're going to, for B, determine the theoretical yield of the acetone we would get if we use this much isopropyl alcohol. So divide by the molar mass of isopropyl alcohol, and then we're going to convert from moles of isopropyl alcohol to moles of the acetone. So 3 moles of isopropyl alcohol react to give us 3 moles of the acetone. So then multiply by the molar mass of the acetone to get the mass of acetone that is obtained. So then use percentage yield is equal to actual yield divided by theoretical yield times 100. So your theoretical yield is how much we calculated, so put that on the bottom, and then we end up getting the percentage yield. So for C, we are going to find the empirical formula. So all of the carbon is in the CO2 and all of the hydrogen is in the H2O. So convert milligrams to grams and then divide by the molar mass of CO2 to get moles of CO2. So then in 1 mole of the CO2, we have 1 mole of carbon. So now we can convert from moles of CO2 to moles of carbon. Then multiply by the atomic mass of carbon. So from that, we get the mass of carbon that was initially in the compound, and we convert that to milligrams. We do the same exact thing with the hydrogen in H2O, except in 1 mole of H2O, we have 2 moles of hydrogen. Then we can find the percentage composition. So we're going to take the milligrams of carbon divided by the mass of the total sample times 100, and that is percentage of carbon. We do the same for hydrogen. And then because we need 100% total, the remaining percentage must be oxygen. Now assume 100 grams of the compound. Then we're going to convert the percentages into masses. So with 100 grams, the percentages are equal to the grams of each of the elements. So then divide by the atomic masses of the elements to get the moles of each of the elements. So now divide by the smallest number of moles to get the subscript on each of the elements in the empirical formula. So we end up getting C6H14O. Now for D, we need to realize that this byproduct is a non-electrolyte based off of the chemical formula, so Van Hoff factor is 1. We need to solve for the molality. So the normal freezing point of benzene is 5.48 degrees Celsius. So we need to find out by how much did the freezing point change. So we find that it changed by 0.61 degrees Celsius. So now we know delta T, or how much the freezing point has changed. So we're going to plug it in it for delta TF, and then we set it equal to the freezing point depression constant times molality times 1. So now we can solve for the molality, and then we get the molality. So this is the moles of the solute in 1 kilogram of the solvent. So now we need to find the mass of the solute in 1 kilogram of the solvent. So by dividing the mass in 115 grams of benzene, we can find the mass in 1 gram of benzene. So then we can then convert grams of benzene to kilograms, and then we find that we have this many grams of the solute and 1 kilogram of benzene. So now that we know the mass in the moles of 1 kilogram, we can find the molar mass. So molar mass is gram per mole. So take the mass and divide by the moles, and we get the molar mass. So now calculate the empirical formula mass. Then divide the molar mass by the empirical formula mass, and we get approximately 1. So therefore, the empirical formula is equal to the molecular formula.